This video was brought to you by the ILC. Hello there once again, welcome to episode 45. Last episode we talked about how to solve a system of equations using a matrix. Now this episode we have inconsistent and dependent matrices, which look a little bit different than the matrices that we solved last time. Let's go ahead and have a look at them. Alright, here's the matrix we have for the first problem. 1, negative 147, 0, 135, 0, 267. Looks just like an ordinary matrix. Now we cannot see yet that this is an inconsistent matrix. Right now it just looks like an ordinary matrix, and the reason why is because it's not in row echelon form yet. So what we have to do first is take it into row echelon form. That means that these numbers in the lower left corner are all going to have to become 0. We can see that 2 of them are already 0. The third one needs to become 0 now. Because it is in row 3, the first thing we will do is change row 3. That is 0, 2, 6, 7. Our target is this 2 here. We need to make it into a 0. And the opposite of 2 is negative 2. So what we need to do is add something multiplied by row 2 in order to get a negative 2 here. We can see in the second position we already have a 1, and we know that 1 times negative 2 would give us the negative 2 that we want. So we'll take negative 2 times everything in row 2. So negative 2 times 0 is still 0. Negative 2 times 3 is negative 6. Negative 2 times 5 is negative 10. 0 and 0 makes 0. 6 minus 6 makes 0. 7 minus 10 makes negative 3. Therefore, our new matrix goes like this. The first and second rows do not change at all. We do nothing to them. But our new row 3 is now 0, 0, 0, negative 3. If we want to solve the matrix, we would have to start from row 3, just like in last episode. But row 3 says that 0 on the left is equal to the negative 3 on the rightmost column. We know that 0 is not equal to negative 3, and this is a false statement. Anytime you have a false statement in your matrix, that's called inconsistent. We would say that this matrix is an inconsistent matrix. And any inconsistent matrix has no solutions at all. The matrix simply can't be solved, and it's good enough just to say no solution. This will happen anytime you have a bottom row that has all zeros except for the last column, where you might have some other number. Now let's look at the other example, dependent matrices. This matrix is very similar to the last matrix we did, except for I've changed the number in the bottom right corner. And as you're going to see, that's going to change everything. Once again, we're going to try to go to row echelon form, and our targets are the numbers in the lower left corner. That is, the 0 here, the 0 here, and the 2 here. Now, we have 2 zeros already, we just need to make the 2 into a 0, so just like last time, we are going to change row 3, 0, 2, 6, 10, by adding, just like before, negative 2 times row 2. So we take negative 2 times each term in row 2, 0, negative 2, negative 6, negative 10, just like it was last time. If we do our operations now, we'll have 0 and 0 makes 0, 2 minus 2 is 0, 6 minus 6 is 0, 10 minus 10 is 0. So our new row 3 is all zeros. Here's what our matrix looks like now. 1, negative 1, 4, 7, 0, 1, 3, 5, and now all zeros in the bottom row. Anytime you have all 0, you have what's called a dependent matrix. To write the answer to a dependent matrix, we're going to do something a little bit different from usual. We are going to skip row 3 entirely, and instead start with row 2. Recall that we have x, y, z, and constants here on the top. Row 2 says 1y plus 3z equals 5. Now we are only going to worry about solving for y. We're just going to leave z as the letter z, and we'll subtract 3z from both sides. We'll cancel out 3z, and so y equals 5 minus 3z. Now we will go to row 1, now that we know what y is. Row 1 says 1x minus 1y plus 4z equals 7. This time we are going to be solving for x. Let's box it in, and we'll just move everything else over. So we'll add y to both sides and subtract 4z from both sides. The y's cancel out, and the 4z's cancel out, leaving us with x equals 7 plus y minus 4z. Once we're here, we can substitute the y that we just found. So y is actually 5 minus 3z, and we'll place it here for this y. X equals 7 plus 5 minus 3z minus 4z. We can simplify the 7 and 5 and the negative 3z and the negative 4z, and so we'll end up with x equals 7 plus 5 is 12, and then negative 3 and negative 4 makes negative 7z. So in our final answer, we'll write this. For x, we'll write 12 minus 7z. For y, we'll write 5 minus 3z. And for z itself, we don't have to do anything. We can just write z. And that is good enough for our answer. Now, just as a word of caution, some instructors will try to replace the z with the letter t instead. That's simply more of a matter of tradition, and you don't need to worry about this so much until later on. If you write z for the purposes of Maths 171, that's fine. If you want to replace it with t because your instructor likes that better, that's also fine. We would just say 12 minus 7t, 5 minus 3t, and t, just instead of z. But as far as this class is concerned, the solution I've written here is okay. Thank you all for watching. We'll see you again next episode.